if we want to think about what happens when we turn a spring on its side, we need to start by thinking about the forces and then work a little bit through the math. So the idea is that we used a horizontal spring as our kind of standard physics model for simple harmonic motion. And in the case of a horizontal spring, we only had to think about one force, the spring force. Now we've actually turned it sideways. We need to think about both the spring force and gravity. So one thing to think about, the starting point, is changing our equilibrium position. So if we have a spring that is unstretched to this length and we add a mass to it, we know that it's going to extend downwards. And the reason for that is the force of gravity. That if this mass is sitting still in place, we know that F net in the y direction is equal to 0. We have a spring force up and a gravitational force down. So there's some stretch that occurs for this spring force to exist. And we can go back and think about the math of what's happening here. So in general, the spring force is negative k times delta y, and that delta y is the shift from equilibrium. So in this case, we've shifted it down delta L. So be careful here in that we have to get the signs right, and we would define up to be the positive y hat direction. So our delta y is negative because we've pulled it down. Well, because of that, this minus sign cancels with that minus sign, and we're left with positive k delta L, and that tells you that your spring force is up, which is exactly what you would expect. We then can say that our net force in the y direction is going to be the y components of each of these forces, and we say that we have k delta L up, positive, and mg is down, which is then going to be subtracted. If this is sitting still, so right now we're not talking about oscillations, we're just talking about it sitting still in equilibrium, we have a net force of 0. So we then use the fact that this 0 must be equal to k delta L minus mg to find what delta L is equal to. It's then going to be mg, our force of gravity, divided by k. So what this has done for us is told us where our new equilibrium position is due to the force of gravity. Another way to think about this, instead of taking an unstretched spring and adding a mass, you could basically turn on gravity. Had there been no gravity initially, this mass would have been sitting up here. What pulls it down is gravity. So that's another way to think about this. You can either add the mass or you can turn on gravity. So now what we want to do is think about how this is going to change our oscillations, given that we have a new equilibrium position. So now we want to think about the forces around that new equilibrium position, and note that we're defining y equals 0 to be the equilibrium position when the mass is there. That's always the coordinate system that we want to use. So in order to think about oscillations, we want to displace our mass a little bit and think about what the resulting force is. So in this case, we've displaced our mass from 0 up to y. Now, in this case, we want to say what the spring force is. And now we would say that the spring force, and in this case, we're actually thinking about from the original stretch. Now our stretch is delta L minus y, because we had said that we had stretched it down some delta L to the new equilibrium position. So let me actually make that a little more clear. We would go down to the 0, sorry. So we've stretched it some amount, and now we're saying, oh, it's stretched less. It's delta L minus y because we've gone back up. So then we say that once again, we want to look at our net force in the y direction. We also have a force of gravity. So my spring force is this delta L minus y, and my gravitational force is mg as always. So all we can do here is rearrange a little bit, right? We don't actually need to do any fancy math yet. We're simply distributing k, rearranging. And now remember that how we had actually found that delta L was by saying that this is equal to 0. That when our spring is stretched delta L, that's where it was in equilibrium. So this term here is 0. And that means that these terms just basically cancel with one another. and we're left with the F net in the y direction is negative ky. So why does this matter? What we then see is even though we have in fact created this new equilibrium position, we actually can just think about our oscillations around it just as before. That F net in the y direction is going to be mass times acceleration. Acceleration is the second derivative of position. In this case, position is in y. So if we divide both of these sides by m, I have acceleration here, which I can rewrite as the second derivative. And on this side, I have negative 1 over m, again coming from force, times ky. So the reason this matters is that this you should be able to recognize as the equation of motion for simple harmonic motion. And so we've talked before about how the solution to this differential equation is cosine with both an unknown amplitude, A, and a phase constant that comes from your initial starting position, and that the omega is going to be given by the square root of whatever you have out in front, which in this case is k over m. And that is exactly what it was for a horizontal spring. So the takeaway message here is that when you turn your spring from horizontal to vertical, you haven't changed the frequency of oscillations, this frequency here. You haven't changed your period, t, which can be calculated from this. All you have done is changed where your equilibrium position is. So vertical oscillations actually just like horizontal oscillations, just with a new equilibrium position.